Okay. Says the recording has started. But the session chair isn't yet here. So we'll wait for a little bit, and if he doesn't show up within the next minute or so, then I'll try and reach him. Fabio, are you able to see like a play video button at the bottom there, or no?
I have a stop camera and the start sharing screen.
Mm-hmm. Okay. Then.
Or play a video. No, I have a play a video.
Okay.
No, but then I can also share this. I think if I share the screen, that will work.
Yeah, it would work, but I still would like to wait for the session chair, Miguel to show up, but see if he is on his way.
I think you should be able to see that.
Yeah. We
okay.
definitely.
Then it works.
Mm-hmm.
Because then you can play the video. I think this would work.
Okay.
If Felix doesn't join, then I'll do this.
Okay. I see him here.
Okay. So welcome to the Program Analysis 4 session. I'm sorry, we were in a different room. So we have a set of 5 talks in this session. I would encourage you to write up some questions as we go along in the chat. And then we can ask them in person, but just for me to know which questions are in line. Okay, so the first talk is by Lingui Lu. I'm not sure if it's... Hi. So we were really on the different room. So
the first paper should be a video, I think. I don't know if the presenter's here for that. But Fabio said he could play a video for the first paper.
Okay.
Yeah, I think I can play the video for that. Felix prepare for this. So this is the 5 minutes video. That should be okay.
Okay,
You want me
sure.
to start sharing?
Yes, please.
Yeah, it works.
Okay. Yeah.
Okay, so let me start.
Hi everyone, my name is Felix Paul.
Sorry.
Well, I'm here.
He's here. Yeah. He's here because I saw him earlier.
Yeah,
So
we were in
please.
the same room, but
Yeah, exactly.
kind of like difficult to get over here if it is the same link.
Yeah. Okay, so please, Felix.
Okay.
You can do it.
Yes.
Yes. So you should be able to see my screen, right?
Yes.
Okay, then let's go. Hi everyone, my name is Felix Pauk, and together with my colleagues we submitted the paper TaintBench, Automatic Real-World Malware Benchmarking of Android Taint Analysis. So in that context, what is a benchmark for Android taint analysis? Well, consider you have your benchmark app here, and a statement in that app is called a source if it extracts sensitive information. Here in this example, there is one source that extracts the device's location and another source that accesses your contact data. And then in the same app or another, there might be a sink that somehow leaks your information by uploading it to the internet, for example. And the benchmark in that context consists out of dozens or hundreds of these benchmark apps. And for each of these apps, we have to document the expected and unexpected benchmark cases. So in this case, we have one expected case. So the context source is actually connected to the sink. And we have one unexpected case, which is the second benchmark case we would have to document for this benchmark app. So the location source is actually not connected to the internet sync. So if a tool would find that connection, that would be considered false positive. Having this definition of a benchmark, we came up with our first contribution, the TaintBench suite. So we started off with the Contagio malware set, which contains more than 300 apps, and ended up with 39 benchmark apps that we included into our final TaintBench suite. For these apps, we documented almost 250 benchmark cases, of which roughly 200 are expected cases, and the remaining are unexpected cases. The whole benchmark, along with various information and possibilities to inspect all the cases, is available on our GitHub website. The second contribution of our TaintBench study is the TaintBench framework that supports you with 3 different phases of benchmarking. First, with the construction. So we added to JUDX a plugin that allows you to document taint flows right in the IDE. So you can click on sources and sinks and define the intermediate steps, and then you can just output that as a ground truth or baseline definition for your benchmark app. The second phase, evaluation. For this part, we extended RepoDroid such that you can automatically execute the benchmarks you created in the first step. And lastly, we wrote a Visual Studio Code plugin that allows you to inspect what you have constructed as a baseline for your benchmark and to inspect the actual result that were output in the second phase during evaluation. And of course, you can also compare what was defined in the baseline and what was actually output during the evaluation. Having the suite and the framework, we conducted some experiments to check if we can gain more knowledge via our TaintBench suite. So here we see the accuracy metrics, precision recall, and F measure for DroidBench, a state-of-the-art micro benchmark, and TaintBench, which is our new real-world malware benchmark. And if we take a look at Amandroid here in terms of precision, we already see that the precision value drops if we switch from DroidBench to TaintBench. And with respect to recall and F measure consequently, this becomes more obvious for Amandroid and FlowDroid. So probably these tools are over-adapted with respect to micro benchmarks. To further investigate that, we performed more experiments. So here we see the results for 2 different experiments dealing with DroidBench, and we increased the adaptation to the benchmark. So in the first experiment, we used the tools in their default configuration, and in the second benchmark, in the second experiment, we over-adapted on purpose the tools such that they perform particularly good on the benchmark. And as we can see, the precision values are slightly increasing in case of DroidBench. We did the same for TaintBench. There we have more levels of over-adaptation. And well, let's skip precision for now because it's a little bit counterintuitive, but let's have a look at recall and F measure. Here we can clearly see that the accuracy metrics go higher the more over-adaptation we do. But still, in the end, if we compare DroidBench and TaintBench, we see that the accuracy drops. So even though we do this on purpose over-adaptation, the tools still seem to be over-adapted to micro benchmarks. Additionally, what we can certainly say is, having that picture, that sources and sync lists are actually crucial. The results of the taint analysis tools highly depend on these lists. And there is no perfect list. We got a second finding that is visible in these charts here. Again, the dark green bars stand for DroidBench, and the light green bars we will see later are for TaintBench. And as you may have noticed, on the x-axis we have Amandroid, Amandroid asterisk, FlowDroid, and FlowDroid asterisk. The tools marked by the asterisk symbol stand for the newer versions of the same tool. And if, as we already can see in case of DroidBench, is that in case of Amandroid, the precision metrics drop when we switch from the old version to the new version. So that's a regression. For FlowDroid, we cannot see that. But if we include TaintBench, we can see the regression for both tools, for FlowDroid and Amandroid. So everywhere we got these regressions, which are very visible with TaintBench. That's it already. So I briefly presented the suite, the framework, and the evaluation we conducted with it. All that is available on our website. So I'm really happy to answer your questions later on or to see you in Pittsburgh.
Thank you for this great talk. Our next speaker is Marcel. So if you can please share your screen. Thank you.
Can you hear me? Yeah. Okay.
Yes.
So that's great. Thanks, Felix, for this great talk, because this is going to be a motivation for my talk. So my name is Marcel Böhmer. I'm a faculty member at the Max Planck Institute for Security and Privacy in Germany. And my talk is about statistical reasoning about programs. And this is a near paper, so it's not a full paper, it's a short paper, but it gives essentially a vision of what we can do to analyze programs. So how do we analyze programs these days? So what we do is we use formal reasoning. So to formally reason about a program means to interpret a program's instructions according to the given semantic rules. So a program is simply a set of instructions, and a programming language essentially comes with rules about structure, which are called syntactic rules, and rules about behavior, which are called semantic rules. So to interpret instructions according to a given set of semantic rules means to interpret each instruction, right? So, and then the formal reasoning means to derive a model of computation that then describes the relationship between the inputs of that program and the outputs. And program analysis is about computing a certain property of interest. Does there exist a bug, for instance? And so this property of interest is then computed within this model of computation. So I've visualized this here a little bit. You have the source code, you have this like a static analysis. You could also do this with a dynamic analysis, where you simply have execution traces, like traces of instructions. And so this analysis then builds via formal reasoning, and using these semantic rules builds this idea of how the program behaves for all inputs, right? So this idea is called model of computation. On what happens in reality is the program source code is being compiled and linked, and then you get a binary, and this binary is then being executed by the machine. And so a problem of reasoning within this model of computation versus actually reasoning within the actual computation is that you get this gap, right? This is an abstraction. Often we trade for scalability. We have very, very big tools these days to analyze very large programs. We trade for the scalability. We trade soundness or completeness. That means this model might even be incorrect, or it might be incomplete. And compiler, for instance, sometimes the semantic rules are not complete themselves, so the compiler resolves this undefined behavior, and so the program actually does something which the program might not have been intended. So there's this gap, and this is the gap that I want to address. So of course, I just wanted to reiterate that static analysis and dynamic analysis are really, successful. You have analysis tools that analyze programs at a very large scale and that are being used in industry to find bugs that are very security critical. You also have this. You have very many success stories in formal verification. For instance, SEL4 is this project where they verified an entire operating system microkernel. So it's important to do formal reasoning, because you can reason about all inputs of a program. But at the same time, what we lose is guarantees. Because of this gap between the model of computation and the actual computation, you report bugs that don't exist, false positives, and we do not report bugs that do exist, false negatives. So the earlier talk was about measuring false positives, and the next talk later by Akshay is going to be about somehow engineering away these false positives. But we don't need to. We don't need to deal with this false positives at all if you just use the execution itself. So what we get what the problem is here, we can't seem to quantify the degree to which our analysis is incorrect. Right? Static analysis and dynamic analysis is incorrect, but we don't know to which degree. That's why we need benchmarking, by the way, Felix. And so my proposal is to use some kind of scale-oblivious sampling based in vivo program analysis. So in the observational setting, you simply randomly sample a property for a set of executions, a random set of executions. In the experimental setting, you would then modify the execution and essentially have a shadow execution and compare values across this shadow execution to reason about properties of your program. You use actual executions and then use statistics to extrapolate from the properties that you have observed in your sample execution to properties of the population of all executions. And you can do that with quantifiable accuracy, so you get some kind of statistical sense of your guarantees back. And you can do that for systems of arbitrary size. And the positive thing is about statistical reasoning is you can always you can always trade better efficiency for a lower sampling rate. And with this trade, you can still retain these guarantees, these statistical guarantees. So in my roadmap, I point to many statistical challenges and also a lot of opportunities that this approach provides. But what I think is, apart from this formal reasoning kind of perspective on program analysis, I'm suggesting to take statistical analysis, statistical reasoning as a new lens for the program analysis problem, because measuring properties of a systems of arbitrary size, it doesn't really matter how large these systems are, and measuring degree of uncertainty about these facts is the backbone of statistical analysis. And that's it from me. Thank you.
Thank you for this really thought-provoking presentation. The next presentation now is by Saikait.
Yeah, let me share the screen. Okay, can you see my screen? Okay, let me start.
Yes.
Okay. Hi everyone, I'm Saikat. I'm a PhD student at UIUC. So today I'll be presenting a paper, InspectJS, which is an approach for leveraging code similarity and user feedback for effective taint specification inference for JavaScript. This is a joint work with Diego from UBA, Shubhendu from MSR, and Max from GitHub. So it is well known that web applications are often plagued by potential security risks. Some examples include attacks like NoSQL injection and cross-site scripting. JavaScript is the most popular language that is used to build web applications. Hence, if we can develop techniques to ensure that JavaScript programs are free of such vulnerabilities, then we can also make web applications safer. Taint analysis is a branch of data flow analysis that can be used to detect such security vulnerabilities in programs by detecting flows between untrusted and sensitive program points. However, taint analysis in most cases also requires some specification, known as taint specifications, to indicate what are those untrusted or sensitive program points that we need to analyze. So taint analysis can be used to detect violations to various security policies. Some examples include integrity policies that forbid flow from untrusted sources to sensitive sinks, such as making database queries, and confidentiality policies that forbid flows from sensitive sources to untrusted sinks, like entering a password. However, to check these policies, we need to specify what are these sources or sinks or sanitizer APIs that are used in the code. Sanitizers are functions that prevent unsecured data flows between a source and a sink. Developers often do this task manually. For instance, they may use the API documentation to figure out what are the taint specifications. However, as you can imagine, this is a very labor-intensive task, and it can often lead to incorrect or incomplete labeling. Hence, our goal in this work is to answer the question, how do you automatically infer taint specifications that are currently missing that can complement the manual models that developers already use? The inferred specifications can then be integrated into a static analysis framework like GitHub's CodeQL to improve the manual models. To address these challenges, we developed InspectJS. InspectJS is a machine learning-based approach for inferring taint specifications for JavaScript libraries that can complement the manually modeled specifications. At a high level, it takes some seed taint specifications and a set of training projects as input. Then it learns a new set of specifications and uses them to detect program elements in the test projects. InspectJS also incorporates developer feedback to further refine the predictions. In this work, we focused on inferring sinks since they are often library specific. We do not infer sources since they are often shared between libraries. And all the unknown functions are already considered sanitizers by default in the CodeQL library. Hence, we do not consider those. So there are three key phases in InspectJS. Our first component, Seldom Star, frames the problem of learning API roles from its usages in training projects as an optimization task. Then it uses the learned specifications to infer sinks in the test projects. In the second step, we use code similarity-based refinement step to further filter out false positives and improve the precision of predictions. And in the final step, we leverage user feedback to further refine our predictions and allow developers to quickly triage through all the predictions. The inferred taint specifications can then be easily combined with the manual taint specifications in a static analysis framework like CodeQL to boost taint analysis and improve the vulnerability detection. Let me now quickly summarize the results. So we use InspectJS to predict sinks in libraries from three popular CodeQL security queries, NoSQL injection, XSS, and tainted path. Using Inspect.js, we were able to find new sinks, that is previously unknown sinks, in all the 3 queries. And using these, we sent 3 pull requests to CodeCube developers to augment the existing models with the new sinks. And these have already been accepted by the developers. However, we also observed that the raw predictions that we obtained from SendStar had low precision and required a lot of triaging. In this aspect, our code similarity-based refinement step helped a lot. It helped us reduce the triaging effort by 1/3. In the future, we are also working on expanding our approach to new security queries, inferring source specifications, and also developing specialized embeddings to improve the refinement step. That brings me to the end of my talk, and I'll be happy to answer any questions later on. Thank you.
Thank you very much for this really nice talk. The next speaker is Akshay Utu. So please, you have the floor.
Right, can you see my screen?
Yes, perfect.
Okay, yeah.
Yeah.
Thank you. So yeah, my name is Akshay, and I'm going to be presenting our paper, Striking a Balance, Pruning False Positives from Static Call Graphs. So here is an oversimplified view of how a static analysis pipeline might work. So we have a program which is fed to a call graph construction tool. So a call graph construction tool is itself a kind of static analysis, and it produces a call graph, which is a graph of all the possible method calls in a program. And a client analysis, like a null pointer analysis, is typically built on top of this call graph. And then it produces its null pointer once. So to quantify how well the analysis is doing, we typically define 2 metrics. That's precision and recall. So precision is defined as out of the static analysis warning or edges, how many were true positives. And it can be thought of as 1 minus the false positive rate. And the recall is defined as out of the ground truth errors, how many did the static analysis catch? So the important point here is that the precision and recall of the call graph can directly affect the precision and recall of the client analysis that's built on top of it. So let's look at one issue with current tools. And so user studies that take a survey of developers on their expectations from static analysis tools conclude that these tools should aim for 80% precision. But current call graph tools like Wala, which is one of the most popular Java analysis tools, gets a precision of 24% and recall of 95%. And here we assume the dynamic analysis to give the ground truth. So why is Wala designed this way? And the simple answer is that it was designed as a recall-focused verification tool. But there's certainly a gap between what Wala provides and what users expect. So what can we do about this? And here's a brief overview of our solution. So a program is fed to a call graph construction tool as usual, and it gives a call graph with 24% precision and 95% recall. And at this point, we feed it to a new unit called the call graph pruner, which is going to prune away mostly false positive edges and a few true positive edges, and give us a call graph with 66% precision and 66% recall. So we'll take a little deeper look at the solution. So we can roughly break it down into 2 components. The first component is a classifier generator. So this is going to be an automatic ahead of time process, a learning process to generate a classifier. And you can think of the classifier generator as a function that takes in 3 inputs: a static call graph constructor, a dynamic call graph constructor, and a set of training programs, and outputs a classifier. And the classifier is used in the second component, which is the call graph pruner. So the call graph pruner, which we saw in the previous slide, can be thought of as a function that takes in 3 inputs: an existing call graph, a learned classifier, and a threshold, and outputs a pruned call graph. So the threshold here is a parameter set by the user to decide how aggressively the call graph pruner should prune edges. And finally, even though we know that the call graph pruner improves Wala's call graph precision from 24 to 66%, we're also interested in knowing what effect this has on a client analysis, like a null pointer analysis. So we ran this with a null pointer analysis. So we ran a null pointer analysis with the original call graph and got 27% precision. So one can imagine how a programmer would not like such a tool that has 3 out of 4 errors as false positives. But when run with the prune call graph, it got much fewer errors, but it also got 77% precision. So at this point, a lot of the errors are true positives. And that's about it for this talk. Thank you for listening.
Thank you. Thank you. I think next is Mohammed.
Yes, let me share my screen. Okay. Can you share?
Yes, perfect.
Yes. Hello, everyone. I am Mohammed Wardat, a PhD candidate at Iowa State University. Today, I am going to talk about our paper, Deep Diagnosis. This collaborative work with my advisor, Dr. Reddish Raja, and co-advisor, Dr. Willie, and Dr. Bruno Dantes Cruz. Deep learning is being used in several safety critical applications. Because of that, bug can have a big impact on the user's life. Thus, testing and verifying systems that use deep learning is very critical. In this work, we aim to improve the reliability of deep learning application by diagnosing bugs and providing fix suggestions. A developer working on the following code. The code is for a sequential model. Unfortunately, the code is having low performance during the training, and the developer don't know how to solve the problem. Because of that, he decided to use Stack Overflow to ask the following 2 questions. Why do I get a bad result for a simple data set? Is my data set malformed? As a researcher, I try to help the developer and run the state-of-the-art tool on the code. The result are as follows. When using Omelette, the training was terminated without identifying any bugs. When using Deep Localized, the training was terminated and it indicates that there is a numerical bug on layer 7. When using AutoTrainer, the training was terminated and it is not able to fix the problem. Unfortunately, none of those techniques can answer the developer's question and indicate how to fix the bugs, thus indicating that additional research is needed in this. Existing technique propose different analysis method to detect bug in the deep neural network, but they don't correlate symptoms and root causes. They don't detect the bug that manifested as a trend of value and don't offer possible fixes. To fill this gap, we propose deep diagnosis, an approach that maps symptoms back to their root cause. To that end, this work make 3 contributions. Study different type of symptoms and propose dynamic analysis approach for detecting and providing possible solution to fix. An evaluation on 444 big model from real-world neural network and prior work demonstrating the effectiveness of the approach compared to prior work. The result shows that our prototype is more effective and efficient than. This figure provides an overview of our approach, which contains 3 parts. Left part, the approach started by run initial model and pass our callback method. Middle part, this callback allow capturing and recording the key values such as weight, gradient during feed-forward and back propagation stage. A dynamic detector is applied to report different type of symptom, such as a denoid saturated activation function, based on the error condition that we define. Right symptom is detected. The approach will analyze the recorded key value and determine the best location in the original model to fix the problem. we propose a decision tree to map symptom to fix. The main goal of the decision tree is to mitigate the manual effort and reduce the time for diagnosing and fixing the bugs by mapping the path from the root to one of the leaf. The decision tree consists of 24 rules which map symptom into one of 7 classes of changes. In this work, we aim to answer the following research questions. We cover research question 1 and 2 in this talk. For research question 3 and 4, please see our paper. Research question 1, can our technique localize faults and report their symptom in deep learning program effectively? Research question 2, how effectively and how fast can our technique localize faults and report the symptoms compared to existing methodologies? To answer research question 1, we compare deep diagnosis with the auto-trainer, deep localize, and omelette. Our result shows deep diagnosis can successfully detect a different type of symptoms and report actionable change. It outperformed these tools. To answer research question 2, we evaluate the efficiency of deep diagnosis in the term of the performance. We measure the analysis time for the deep diagnosis and other state-of-the-art tools for a source of the benchmark from Stack Overflow, GitHub, Scopus paper, and AutoTrainer benchmark. From the figure, deep diagnosis has lowest runtime in the Stack Overflow and the Scopus models, but it has higher runtime compared to the Omelette and on the GitHub models. Deep diagnosis is faster than AutoTrainer on all benchmark except for the blob and circle dataset. In conclusion, we propose a dynamic analysis approach to detect error and receive useful message for DNN bugs. Our result shows that deep diagnosis outperform the state of the art, and more description can be found in our paper. Thanks a lot for attending the presentation.
Thank you, Mohammed, for this really nice presentation. Now I can open the floor for the discussion. And the first question is by Akshay. Question for Felix.
Yeah, my question was, why is recall poor for Amandroid or Floatride? Like, I know this is a little orthogonal to your research focus, but do you have any insights as to what taint flows or program constructs that these tools find hard to deal with?
Yes, so to answer that question first, we had the adaptation of sources and sync lists. So in the first version, we used the default list, and we found out that the intersection, for example, between the DroidBench sources and syncs, so the syncs that appear there and the sources and syncs that appear in TaintBench, are very different. So that was one of the steps where we did this on purpose over adaptation. And once we had the equal source and sync lists, recall already went up. But with respect to the final results we got, as you said, that was not our job to look into that. We were just building the benchmark. But from what we know is that the main reason is that the call graphs are incomplete. So often, for example, libraries are used and they are not correctly modeled in the call graph. And that's the simple reason why the taint flows are missed.
Okay. So the next question was by Fabio to Marcel.
Hi, Marcel. It's a very nice talk. So I put the question also in the chat. So I like the idea of using statistics, but one of the problems that statistics has is that they like normality. And statistics also like independence of errors, similar things. But when you have 1 million instances or something like this, then you will have that all the programs that have the same input will fail at once. So statistics independence is violated. So you will have lots of this problem. Maybe 1 million instances are even not normally distributed. We have several instances that are a copy of the same. So how do you think that people will be able to manage this when the traditional statistical tool will not be useful?
So my answer to this is it's an open challenge. I put this out as something which we should investigate, particularly to address that false positive and false negative problem in static analysis, at least to provide another kind of perspective on this. And so so you put it nicely. You said that statistics normally assumes independence, and so the assumption that they often have, and that we kind of require here too, is IDD independent. So all the executions are independent and identically distributed. The samples that I take are independently and identically distributed, which means independent means the executions are independent, and identically distributed means that the executions that I see today should be the executions. The probability of observing this execution today is the same as observing the same execution tomorrow. So this probability doesn't change. This is an assumption, and that makes statistics easier when you make these assumptions. But of course, there are also statistics that that investigate cases where this is not the case. For instance, in machine learning, machine learning is very much has the same kind of problems that we would see here in program analysis as a statistical problem. For instance, a big topic in machine learning is distributional shift. Suddenly, samples that training samples that you have currently don't match the kind of validation or kind of the samples that you would see in reality. So you have a self-driving car, you train it on a certain set of streets, and when you take that self-driving car to a different set of streets, then the classification doesn't work as well. But these things can be studied, and I think being open to exploring these kind of challenges, and particularly statistical challenges, are interesting both from a statistician's point of view as well as from a software engineering point of view.
Okay, Daniel, I think you also had a question for Marcel.
This is also a question about this work. So I'm wondering about what the process of sort of writing a spec and validating and sort of iterating on a spec looks like in a statistical world, right? Because often you write a spec and then you find a counterexample and you sort of keep iterating on the spec until it converges. I'm wondering what that looks like in the statistical model, the statistical world.
So and the proposal that I make is not to substitute static analysis or dynamic analysis, statistical reasoning, but to provide an additional tool. So an advantage of formal reasoning is that you can reason about all inputs of a program. Like when you say you have a specification and then you find a counterexample, you're implicitly saying that you reason about all inputs of a program. Statistical reasoning is kind of extrapolating from samples to the entire input space. So you can't really take that counterexample by reasoning once over your system, right? But saying that, what you can do if you can control the sampling process itself, which is possible, for instance, using fuzzing or using other kind of execution generating mechanisms, if you can search, if you can control the control the sampling of these executions, you can specifically search for the counterexample, like we do all the time in testing. We search for a bug-inducing input. And then you can see whether this violates the specification. So maybe testing is your instantiation of the problem for statistical reasoning without the statistics.
Mm-hmm. Okay, so Saikat, you have a question for Akshay?
Yeah, I had a question for Akshay. Basically, what were you using for the classifier and how did you train it?
Right. So the ML model that we use is random forest, but we don't claim that this is the best model. And the focus was on showing how to cast this as a machine learning problem and how well it does on a downstream task. And regarding how it is trained is we provide it with a large number of static call graphs and with the dynamic analysis providing the ground truth labels. And then we just cast it. We train a feature set. We design a feature set over the static call graph and then train a machine learning model to predict if a particular edge is a true or false positive.
I see. Thanks.
Okay. So the next one was Daniel for the call graph pruner paper.
Yeah.
Right.
Yeah, so it's a question about the call graph pruner. So I'm curious, it seems like right? You're trading off precision and recall. And so I'm wondering how tunable that is. Is this something where a user can basically say, I'd like to give up this much precision in exchange for as much recall, or this much recall in exchange for as much precision? Or is it really sort of like a one shot, you run the tool and you get the trade-off, and that's what it gives you?
Right, that's a great question. And I agree that tunability is really important because different applications can have different requirements of precision and recall. So yes, we do provide a knob. And the way it works is we actually predict a probability for every edge in the call graph, and the user can set a threshold below which we'll prune off all edges. So by setting that probability threshold, the user can decide how much recall they want to trade off for precision.
Okay. So the next question was by Saikap to Marcel.
Yeah, my question for Marcel is, can you comment on how much developer effort will be needed to enable static analysis, basically versus what they're doing today?
Developer effort is very simple. So today you can implement. So in fuzzing, how do you take a program and make it fuzzable for graybox fuzzing? Graybox fuzzing requires a coverage feedback. In order to inject this coverage feedback in an arbitrary program, you modify the compiler, and this is called a compiler pass. So you have a compiler pass that runs and simply injects compiler like coverage instructions into an arbitrary program. So one is you have LLVM passes. Two is you have hypervisors. Hypervisors execute your operating system. You can, for any program that runs on your system, you can observe how these programs run. It doesn't really matter which programming language this program is written. Your hypervisor can kind of inject these probes into your program. So that's all you need is some kind of probes that kind of monitor certain kind of properties in your program, and then you chain together these properties in some kind of a like some kind of a network. This is kind of how I think about this. For instance, okay, here's an example. Earlier, Felix talked about Taintdroid and Taintbench, and so Taintdroid is a way of looking at information flow, finding out whether a program there's an information flow from a sensitive source to a public sink. So we wrote a simple paper which was called Mutaflow, where we take a program and automatically instrument all sensitive sources to spawn off a shadow execution. And in this shadow execution, you would modify the value of the data coming from the sensitive source. Arbitrary, like fast arbitrary data value. So you have this shadow execution and you have this original execution. At any public sink, you simply observe whether there's a difference in values for the shadow execution and the original execution. If there is a difference, then you know that there's an information flow. This is called this is the experimental setup where you modify an execution. And compared to static analysis, you don't really need to know which instructions you executed. The information flow can go through the internet somewhere. You don't care, right? But you know for sure there's no false positives. You know for sure that there's an information flow through this experimental kind of approach. And this is just an instantiation of this program analysis. And what you can do with statistical reasoning is now you can also quantify, so you know you don't have false positives, but you can also kind of, assuming IID, you can also quantify upper bound false negatives. You know when you haven't seen an information flow for a while, and statistics allows you to give you a probability that there actually exists an information flow when you have not seen one.
Mm-hmm. Okay. Yeah, you wanted to add something? Sorry. No. Okay. So Daniel, you had a question also for call graph pruning tool.
Yeah. So, so I noticed that you said you were using a dynamic call graph as your ground truth. And I'm wondering sort of how realistic that is, right? Because often the interesting cases are sort of the unlikely branch, but possible branches in a graph where you often won't see a dynamic trace unless you have good test coverage. And so, do you think this is a problem? Do you think it's
Right. So, yeah, the dynamic call graph as the ground truth is an approximation, and it's definitely a concern. It was definitely a concern when we started out. So the best thing, the best effort that we can do is to we selected from the benchmarks that we already knew had good coverage. And of course, the coverage is still never going to be perfect. We're never going to get the perfect ground truth, but it's as close to it as we can get for the scale of our benchmarks. So in around 140 benchmarks that we had, they had a cumulative of roughly nearly 1 million edges, and we can't get the ground truth for these by manually labeling it. So the dynamic analysis is the only ground truth labeling process that actually scales. And of course, as I said, to make sure that we get a decent coverage, we select only those benchmarks that we already know get good coverage.
Okay, so the next question is by Fabio to Marcel.
Yeah, I think Marcel also answered me in the chat, but then I think it's an interesting discussion. I really like the incomplete flow example, because that's the place where the statistics make sense, because you are basically understanding the fact that you have not seen an error. You've seen an insecure flow and so on. But then it will mostly apply to, I think, to verification, right? You run a timed bench. On all the verification, you conclude then, okay, you get a bill of health from Floodroid, but you know that maybe 30% you don't really know it for sure. So would you think that this will be the case? So we just really use it for, application will be really estimating the real certainty that verification or bug finding will find out, rather than the security or insecurity of the tool. I don't know if this is clear, right? So you think it's more promising as to understand whether the object program is insecure versus understanding how imprecise is the verification program, rather than the object program itself.
So I'm not sure I'm following the distinction between object program and verification program.
So the object program is the program you're verifying, right? You don't know if it's insecure, and but instead of running this 1 million times, you run Floodroid 1 million times on a different project, so that then you will know when you're running on your particular program that you will have a certain uncertainty with high probability, and maybe you will fail to construct an error, so your program may still have an error.
So it's so you have, okay, here's an example. Google currently has a bug finding approach implemented in Android R and in the Android operating system, which is enabled with a certain probability. It's no overhead because it is enabled only with a certain probability, and so you have. I think most of us have a running Android here, or iPhone, or some phone, and so you have 1 million people, or a lot more people, using Android, and so despite the probability that a bug is being reported is very low, because of this large number of executions that you can see concurrently, you get a good signal of how buggy software is that runs on an Android phone. So we don't have any static analysis. So my my concern is even static analysis verification, software verification, reasons in this model and makes this assumption about the program, ignoring the machine. And my concern is that this problem, this gap between the model within which you reason and formally verifies the software system and the actual machine executing our system is so large that now we verify and prove correctness, even though the implementation is still insecure. And so because we can execute a machine and simply take these executions as a sample of all executions, we can provide we have a much better handle on the actual bugginess or any actual property of that property of interest of the system. This is where I see the main benefit of this idea.
Okay, more questions? If nobody has one right now, I maybe would like to ask Mohammed about his work on identifying the causes, the root causes from the symptoms. And I would like, I was wondering while seeing your talk, whether there could be some inspirations that you could take from your work to other kinds of programs. So are there any kind of lessons learned from what you're doing with the deep neural networks that you could adapt to other kinds of programming approaches?
Yeah, our approach is focusing in detecting the bug for detecting the bug in the DNN. If you have any low performance in your approach, you can run our callback, and callback give you the root causes that causes this bug, and they provide for you some suggestion how to fix this, hint how to fix this bug. We are just our approach is focusing in the DNN. We are planning to extend this for another type of model, say like a convolution neural network or LSTML model, which is make it easy for the developer to improve the model that he using for other research.
Okay, thank you. More questions?
Yeah, probably one.
Yes.
With respect to the pruner, you had that slide where you talked about your experimentation results, and if I remember correctly, you had like 200 reports before, and then you applied the pruner, and then it was about 27 or something. That made your precision go up, but the recall go down. In that scenario, in that experiments, where was this knob set to maximum best precision you can get, or was it a trade-off, like in the middle?
Right. So at that point, it was set to around 45% probability. So in our experiment results, we actually provide all possible trade-off points between precision and recall, but we select one of them which has equal precision and recall to do sort of a deeper analysis and to see how that affects a null point analysis. But at that point, it was roughly 45%.
Okay, why 45?
So we just selected that point because it gave equal precision and recall. So at that point, we sort of balanced the requirements between these two competing metrics. But this may not be the best point for all applications. So there may be some applications that need high recall, some that are more precision sensitive. So it's up to the application to pick what point on that trade-off they want to be at.
Okay, all right. Thanks.
Yeah.
Okay, more questions from the audience? No. So maybe one for Felix. I know that in your paper you did have a few more evaluation experiments that you did not have time to cover here in the presentation. Maybe you could take the opportunity to talk a bit about them right now.
Well, so what I mentioned were these 4 different experiments with TaintBench, where we used different level of sources and sinks. So we used like a cooperative approach to automatically adapt the sources and sinks. So we did that for the first case. We used the default one, then we adapted them with respect to a whole benchmark suite, and then we used kind of a cooperative approach and the definition in the TaintBench ground truths to get them for an app level, and in the very end for case level. So we only use the sources and things that actually are used by a single case. But we had more experiments. For example, we built a tool that kind of sliced the program, but it's not a program slicer because it really uses documentation we have for the TaintBench apps. So if we have a taint flow that starts at some source and ends at some sink, we also have got the intermediate steps in between documented. So we could just follow these intermediate steps to do some sort of slicing. And we did that to find out if there are other circumstances in this huge real-world apps that kind of influence the analysis. And the outcome is in the paper that we find new true positives, but also we miss some taint flows. And we, for the last experiments, we used Delta apps. So it's a little bit similar to what Marcel talked about when we talk about Mutaflow. What we did there is we, in principle, destroyed the taint flows. And then we checked, does the tool still report the taint flow, or is it really gone? And that the outcome was that we, in most cases, that if we destroyed, the tools were not finding it anymore. But there were also single cases where issues arise.
Okay. More comments, questions? So maybe one for Saikat. In your work, you have those you collect those triples, including source, sanitizer, and sink candidates. And I would like to know, how do you determine if these candidates are good candidates or not? Maybe you could expand a bit on that.
So you want to know how do we select the candidates?
Yes.
Yeah, so basically sinks we basically consider all arguments to external APIs. So that's the category of program elements that we consider as sinks. For source, we basically consider the outputs of functions, and sanitizers are basically just function calls, external API calls. So these are basically the candidates that we consider for sources, sinks, and sanitizers.
Okay, but how do you know that the function is in the end a sanitizer? Maybe that was my question. Yeah.
Oh, I see. So basically, you're talking about the ground truth, right? So as the final step, once we have all the predictions, so then we allow a developer to basically triage through all the predictions. So in each phase of InspectJS, we have some kind of a score. Like in the first phase, we get some sort of probability that indicates whether a particular program element, how likely a program element is a source or a sink or sanitizer. And then we have other scores based on the similarity. So basically, if we have a predicted sink, then we compute what's the contextual similarity with a known sink that we already have from the seed specifications, right? And then we also have, for each element, we also have its representation, right? Something like that says that, okay, the argument of this particular function is a sink, right? And then we also have a score indicating how general the representation is, right? So basically, how many program elements does that point to? So using these three scores, we allow these, we present these scores to the developers, and that helps the developers to basically triage through all the predictions. So basically, the final ground truth is a developer manually investigating which of the predictions are true positives versus false positives. Right? But all these scores help them easily triage the predictions.
Okay, thank you. So any final questions, comments? If not, I would like to thank all the authors and all the participants in the session for really challenging questions. I think it was a good session. Thank you all.
Thanks, Rico, for sharing.
My pleasure. Okay, bye.